Good afternoon. Welcome to the Astronomy Department cycles of seminars. Thanks for joining us here, also our YouTube channel. And today's speaker is Professor Konstantin Batygin. Many thanks, Konstantin, for accepting our invitation to be here today.
Thanks for having me.
You're very welcome. And I am going to briefly introduce Konstantin. He obtained his PhD degree from Caltech and was a postdoc researcher at Observatoire de la Côte d'Azur in Nice, France, and at Harvard University. And currently, he's a professor of planetary science in Caltech. Professor Batygin is also a singer and a guitar player of the seven-season rock band that apparently is the next Metallica. But today, Konstantin is going to talk about Planet 9 from outer space, a status update. So please turn off your microphones and cameras during the talk, but today Konstantin will be very pleased to answer your questions during the talk. So if you have a question, you can just open your microphone and ask your question. And if you are in the YouTube, you can ask your question, write it down in the chat, and we will ask Konstantin this. And of course, you are also welcome to make questions after the presentation. So, Professor, whenever you're ready.
All right. So, yeah, thanks very much, Maria, for that kind introduction. It's true that I sing and play guitar in the band, but I do both things very badly. And my hope is always that two minuses make a plus, but turns out that's not always true in music. So it'll be a couple more shows before we become next Metallica. I think we have some rough edges to work out. But let's get going. I'll share screen here and go into a full screen mode. Can you see my screen like this?
Yeah.
Yeah. Okay. Fantastic. So it's my pleasure to kind of give a brief update on where things stand with Planet 9. And today I want to talk not just about Planet 9, but about the outer solar system in general, and report on some new results that have come out from collaborations both with my partners in crime, Mike Brown, Alessandro Morbidelli, as well as David Nisvorny and Rosemary Marblin. So just to give an overview of where we're going with this talk, of course, over the last 3 decades, our understanding of the outer solar system has changed dramatically with the discovery, with the realization that Pluto, which is shown here as a blue orbit, is not a single body. Rather, it is a member of a broader population of icy debris that collectively reside beyond Neptune and comprise kind of a second icy asteroid belt of the solar system known as the Kuiper Belt. So what we'll see momentarily are all the, I guess these are not all the Kuiper Belt objects we know of. This is at this point a fraction, but this is a pretty good representative population of Kuiper Belt objects with well-determined orbits, at least as of a few years ago. So the discovery of the Kuiper Belt and the kind of quantification of its dynamical structure has unleashed a bona fide revolution in our understanding of how the solar system, not just the architecture and the structure of the solar system, but also how the solar system evolved. And in particular, the fact that the Kuiper Belt is dynamically hot. In other words, the fact that the Kuiper Belt has a multitude of populations with excited eccentricities and inclinations points to the fact that the solar system planets did not form where they are today, and instead they formed in a much more compact configuration that then underwent a transient dynamical instability. So this is a video of a simulation that is now about 10 years old that we did with Mike Brown about a decade ago, which is a realization of the Nice model, which was proposed at the Observatoire de la Côte d'Azur by Morbidelli and Gomez, Tsiganis and company. And the idea, as I said, is simply that the solar system starts out in a more compact state. And then as the gas goes away and the planets interact with the leftover disk of debris and kind of migrate divergently, they encounter in-motion resonances and the whole thing goes unstable. So within the context of this story, this original population of 20 Earth masses of stuff, of planetesimals that were in the solar system, mostly gets ejected. And what we see today as the Kuiper Belt is just the remaining kind of 0.1%, or even perhaps even less of that original field of planetesimals. So that was back in, I guess, 2011 or 2012 that we did this calculation, and something that we noticed back in 2016, inspired by the work of Trujillo and Shepard, who discovered an object which they named Joe Biden. They clearly had some insight into the future even back then. But something that Mike and I noticed and pointed out is that if you focus on the most distant orbits that exist, that were known at the time within the Kuiper Belt, within the scattered disk subpopulation of the Kuiper Belt, they all kind of point in the same direction and they all kind of lie in the same plane. Now, I should mention that actually the work of Trujillo and Shepard already pointed out that the argument of perihelion of these objects was close to 0. And it was weird that it was not evenly distributed between 0 and 180. And that was, again, like I said, really the inspiration for us to go look a little bit deeper and realize that it's not just, the argument of perihelion, it's the fact that simultaneously the longitude of perihelion, the longitude of ascending node, and the inclinations exhibit grouping within this population. All of this goes to say that the orbits are physically aligned, right? They look like someone arranged them. So that was back in 2016. This is a picture of what the orbital distribution looks like now. And of course, the data set has increased by about a factor of 2.5, maybe 3, depending on where you draw the line of what counts as a distant Kuiper Belt object. And what I want to draw your attention to here is that as the data set increased, something dramatic has happened. Namely, it's an additional pattern which has emerged is that this clustering that was evident by eye in the previous animation is emphasized only among dynamically stable objects, right? Objects whose orbits don't really do anything, don't strongly interact with Neptune, they just slowly precess. So these are objects like Joe Biden that I mentioned before, like Sedna, right, that have perihelia, closest approach to the sun, which is so far beyond 30 AU that they just kind of slowly precess. And conversely, objects that are strongly interacting with Neptune, that are chaotically being advected in their perihelion, that diffusing in semi-major axis, etc. These are objects which don't show a strong clustering at all. So we'll come back to this again momentarily. But one thing that I should point out, of course, right away is that if you see a bunch of clustered orbits in the solar system, especially if they're far away, right? The first kind of question that you might ask yourself is, okay, is this really a big deal? I mean, maybe this was just we know the sun formed in a cluster, so could it be just some passing star early in the solar system's lifetime that perturbed the orbits, and now we just see a remnant of that? And the answer is no. And the reason the answer is no is because these orbits occupy a broad range of semi-major axes. And the differential precession timescale for these objects is a few hundred millions of years. So over the lifetime of the solar system, this clustering, if it was primordial, should have dispersed. Instead, what we see is that this clustering persists, especially among, like I said, stable orbits. And this means that if the clustering is real, then some source of gravity, some kind of gravitational torque is necessary to confine the orbits over billion-year timescales. So back in, back now 5 years ago, we made the case that this gravitational torque, the sustaining, confining torque, is coming from a yet undetected planet in the solar system, and that this gravitational confinement of the orbits actually also simultaneously explains a couple other interesting things about the solar system. So first of all, right, what we found in doing these numerical simulations is that as the orbits get carved out, right, and as a population of clustered Kuiper Belt objects emerges in our n-body models, that same population also experiences oscillations in eccentricity that are coupled to their perihelion oscillations, such that the perihelion gets periodically removed and reattached back to Neptune. And this explains why some of the objects are dynamically stable, and the solar system generally possesses this interesting subset of perihelion removed objects that also show clustering, while the unstable orbits remain kind of rather uniformly distributed. I should mention that in this calculation, of course, what you're seeing here is Uranus and Neptune as the two kind of small pink circles at the center, and the orbit of the unseen planet, planet 9, is the big pink ellipse. And the reason that what you're seeing is a carving out of orbits that are anti-aligned with respect to the orbit of planet 9 is because the way that the dynamics of how this happens is actually an interplay between secular dynamics of planet 9 itself and Neptune force scattering. So what happens is, as the objects kind of process around, when they go through the phase where their orbits are aligned with the orbit of planet 9, their eccentricities reach a maximum. And when their eccentricities reach a maximum, the perihelion gets kind of rammed into Neptune, and then Neptune scatters such objects out of the solar system. This is why the confinement that you see in these calculations is anti-aligned with respect to the orbit of planet 9. I'll also draw your attention to the fact, now that we've gone into the ecliptic plane, you might notice that there's an object that's heavily out of, in fact, a couple objects that are heavily out of the plane. Just make a mental note of that, because we'll come back to this again later in the talk. Okay, so this is all fine and good. But of course, one should always wonder, is this story actually a real story, or are we just making this up, right? Are we being confused by the data? In other words, is the clustering that we see in the distant solar system real, or is it a result of observational bias? This has been a question that has persisted ever since the Planet 9 story has been proposed, and there's kind of, it's a multifaceted question that has taken on a number of different forms. But the key idea of this is, of course, if we are looking for Kuiper Belt objects using a telescope, right, and if we only look in one spot, then of course we're going to discover a clustered population of Kuiper Belt objects, because these objects are brightest at perihelion, so you are favored to discover such a population. So this has been a subject, as I said, of a number of papers, with probably the most sophisticated analysis being done by Napier et al. Earlier this year. And the conclusion of all of these studies is pretty much the same conclusion. The conclusion is, if you take all of these orbits, of which there are, I don't know, something like 15 or 13, or I guess, actually, sorry, I should say, if you take the well-characterized subset of these orbits. I mean, by well-characterized, I mean, you know precisely the pointing history of the survey that discovered them. Then you have 13 objects in total. Okay, this is 13 objects as of 2021. So then you can ask the question of, do all of these objects fall into the high probability region of where the surveys have looked, or do they fall into some offshoot, like low probability region? And what the Napier et al. Analysis basically concludes is that, with the exception of a couple objects which were very unlikely to be discovered, most of these objects fall where the DES survey has looked. And so the DES survey, by virtue of discovering additional clustered objects, cannot actually distinguish between a clustered and a uniform distribution. So in other words, the surveys that have well-characterized biases are so biased that they cannot detect the clustering if it's there. Of course, they cannot refute the clustering if it's not there. Either it's a rather inconclusive result. The way that you can understand why that is this, right? If you look at where, for example, the DES survey has looked, and that's the reason I keep bringing up DES, is because DES has contributed, the majority of new discoveries to the data set. Then the observational signature of DES looks like a tank, right? It's this, I don't know if it's a tank or a battleship, but you know what I mean, right? So then you can ask the question, where does the survey cross the ecliptic plane, which is shown here with the red line? And the answer is in a very specific portion of the sky. And because that's true, you can only discover objects that, in the ecliptic, namely close to the plane of the solar system, right? You're limited to a particular angle. What's interesting is that this kind of by coincidence aligned pretty well with where the original 6 orbits were before DES started looking for them. So DES discovered additional clustered objects, but they don't really mean anything because it can't discover any other object. So doing the exercise in this way, by playing around with 14 or 13 objects, you don't go to a conclusive answer. Okay? So if that's the case, what do we do, right? Well, one way is to do nothing and say, okay, well, we'll just wait until there are 100 objects discovered, and then we'll have to wait for quite a few years. Or the other approach to take is to say, let's drop the survey simulation approach to answering this question, and let's instead do observability analysis. What do I mean by this? When you have 13 objects, when you're playing with 13 or 14 data points, you're of course in this low number, regime of doing statistics. But of course, the Kuiper Belt itself is not 14 objects, right? As I showed in this first or second slide, there are thousands of discoveries in the Kuiper Belt overall. So if we for a second forget about, who discovered what, and just use the power of the fact that if you look at the total, coverage of where people have looked to discover Kuiper Belt object, it actually relatively uniformly covers the sky, then we have an interesting calculation that we can do. Now, importantly, this is different from simulating a survey. This approach to doing the bias calculation basically says, if there is a discovery of some distant Kuiper Belt object with some coordinates, some RA index, and some brightness, that means that somebody looked exactly there, right? And that means that an object of that brightness or brighter was discoverable by the total survey, kind of combined survey of the outer solar system at some point. So then we can take each of the distant bodies and rotate them around every which way and ask, where could the object clones of these bodies, where could they have been discoverable across the night sky? So in this way, we derive a unique kind of bias map for each object. And the answer turns out to be, of course, that there are observational biases. That's obvious. Every survey has observational biases. But then once you have a handle on where they are discoverable, you can ask the question, if you were to populate, to kind of simulate a uniform distribution, how often would you get to see the degree of clustering that you see among the stable KBOs by chance? And the answer is 0.4%. So the false alarm probability of this clustering is about 0.4%. Now, if we were particle physicists, we would say, okay, this is not 5 sigma, therefore it doesn't matter. But thankfully, we're not particle physicists, and 0.4%, or conversely, 99.6% is enough, at least for me to get interested, even to get excited. And I like this plot particularly because this shows the distant kind of high perihelion stable Kuiper Belt objects, and for each one, the color represents where they are discoverable by just observational bias. So in the blue region, you expect to discover them, and overlaid on the back, the red color map shows you where the Planet 9 model tells you they should be. And I would argue that one does not need to do very fancy statistics to kind of by eye see that there's a clear favoritism going on towards clustering in an anti-aligned manner with respect to Planet 9, and not a uniform distribution which is driven by just observational bias alone. So again, please, if there are any questions on this, feel free to just interrupt me, and I will do my best to answer the question so we can keep this maximally dynamic. Okay, so now, provided everything is clear, I want to go back to the request I made when showing you a simulation of Planet 9 evolution, where I asked you to keep in mind that there were those objects that were heavily out of the plane. Okay? And as it turns out, even back 5 years ago, this was already evident. In the data set, there was a population of large semi-major axis objects which appear kind of orthogonal to the plane of the solar system. They fall into a very specific part of parameter space. They kind of look like they're almost on 90 degrees shifted off to the sides of the main cluster and tilted. So Morby and I spent quite a bit of time, my partner in crime, Alessandro Morbidelli, and I spent quite a bit of time thinking about the origins of these objects. As it turns out, the Planet 9 kind of calculation naturally produces them in the right configuration. So we identified a dynamic back in 2017, which is driven not by the Kozai-Lidov resonance, but instead by a different octopolar secular term, which generates a very specific distribution of high inclination objects in the distant solar system, driven by Planet 9. So these are the background, of course, are the simulations. The yellow points are the data that was already available back in 2016. And of course, back when we were figuring this out, we thought it would be cool to catch an object that's transitioning, right? That's transitioning from the main cluster and is on its way to becoming one of these highly inclined bodies. And eventually such an object was discovered. This was discovered by Juliette Becker. Juliette Becker was a graduate student at the time at University of Michigan working with Fred Adams. She's now a postdoctoral fellow at Caltech working in our group. And what she found actually as part of the DES survey was that this object 2015 BP519 was exactly kind of on its way out, meaning it was transitioning from being in the main cluster to having an inclination high enough that it cannot be explained by just Neptune scattering, and is sort of in the right portion of the clustered population. So, of course, discovering one object, in transit is nothing to write home about, and this is by no means any kind of proof that Planet 9 is really out there. It is just yet another hint that hints at a certain consistency that is emerging between the Planet 9 models and the observations that are kind of coming in. I want to focus. I want to say one more cool thing about this high inclination dynamic, which we notice, is that as the objects dance around in the Kuiper, in these simulations in a chaotic manner, of course, as I mentioned, they hug Neptune. One of the things that can happen is they can get scattered out, but occasionally an object gets scattered in. Right? This is because the interactions with Neptune are fundamentally chaotic, and when you come in and your perihelion hugs the orbit, right, you can diffuse in. So we actually discovered that one interesting pathway that Planet 9 instills upon the outer solar system is to take these distant KBOs, right, from the main cluster and send them inwards into the outer solar system with, again, a rather specific orbital distribution. And so when we compare where such highly inclined centaurs lie in perihelion distance, semi-major axis, inclination space, it is indeed rather interesting to note that all of them kind of fall into the regions of parameter space that are populated by Planet 9 simulations. And I would argue that, really individually, these plots are not that profound, but the union of them, the fact that KZ31 and NM56 are both in this almost perfectly retrograde part of the solar system and happen to have the right perihelion distance, etc., is at the very least consistent with the Planet 9 story. So really the lines of evidence for Planet 9 are not just a single clustering of the orbits. The clustering of the orbits, it's the removal of those same orbits in perihelion such that they become stable. It's the generation of highly inclined objects with long periods, and then the kind of transformation of those distant orbits into highly inclined centaurs. So back in 2019, we, having understood the Planet 9 induced dynamics considerably better than what was in the original paper, which kind of in retrospect is embarrassingly primitive, I would say. We sort of redid the analysis and concluded that in the original study, it's likely that we overestimated the parameters of Planet 9, almost all parameters, by a factor of 2. We initially proposed a Planet 9 that was about 10 Earth masses, had a period of about 20,000 years, an eccentricity of 0.6, and an inclination of 30 degrees. And what we find these days is that a lower mass object, about 5 Earth masses, that is somewhat closer in and less eccentric, matches the data better. And I like this quote from the MIT Tech Review, right, saying that given the level of detail, it's easy to imagine that we can point to an area of sky and say, look there, but you really can't. And the reason you can't is because Planet 9 induced dynamics is secular in nature. In other words, if Planet 9 was a ring of mass, the same things would happen. Consequently, we can only use the existing data to predict its mass and the shape of its orbit, right? Things like semi-major axis, eccentricity, etc. We cannot tell you where it is on its orbit because that dynamic is not what's shaping, that kind of short periodic dynamic is not what's shaping the observations. This is in precise contrast to the story of how Neptune was discovered. Neptune was discovered mathematically through perturbations that it exerted upon Uranus by Urbain Le Verrier. And Le Verrier was able to calculate where Neptune was with astonishing precision, precisely because the perturbation was, effectively a synodic one. In fact, if you look closely, Leverrier got both the mass and the orbit wrong by, well, about a factor of 2. Still an astonishing calculation, and nothing. I'm not trying to say anything bad about Leverrier, because to be clear, all I'm saying is that the Uranus and Neptune example was an example where the data allows you to compute the location, not the orbit. Here we're in the precisely opposite regime. So is it entirely hopeless? Well, perhaps it's not entirely hopeless. And I would argue that all bets are on the planetary ephemeris. And this is a plot from a recent paper by Agnès Fienga and collaborators. So what the authors are trying to do here is actually to do something like the Leverrier calculation and use the fact that Cassini, over its lifetime, Cassini spacecraft, not the guy is dead. And actually the spacecraft is also dead, but the spacecraft died more recently. So over the lifetime of the Cassini spacecraft, it completed a large fraction, a large swath of the Saturnian orbit. So using this, Fienga et al. Have been able to, at the very least, put meaningful constraints on where Planet 9 can be in the sky and not violate spacecraft trajectories. So here, they do find an improvement in the ephemeris with Planet 9, but it is marginal. So it's not really a detection, it's more of a constraint. Okay, so all of this is talking about the lines of evidence for Planet 9 and where it can be, but all of this analysis, you might notice, suffers from an important drawback. Namely, every model that I've shown you pretends that the sun is at the center of the universe and the rest of the universe does not exist, right? All the objects that get scattered away just get deleted from the simulation and that's it. But of course, that's not how the sun formed. The sun instead formed in a cluster of stars, kind of like the one that's shown on this slide. And the cluster of stars, the solar birth cluster, undoubtedly must have had some effect on the outer solar system's gravitational structure. So let's think through what that is. Okay? Suppose the sun is embedded in a cluster of about 1,000 stars. That is not just an assumption. That is motivated by the fact that there's an enrichment in short-lived radiogenic species among meteorites, which basically requires the sun to have been, the solar nebula to have been polluted by the byproducts of either supernovae or Wolf-Rayet stars or whatever early in its lifetime, necessitating the fact that the sun was born in a cluster. So if this is happening, and the giant planet, the process of giant planet formation, which remember only takes 3 million years or so at most, if this is happening while the sun is in the cluster, then an undeniable, kind of inescapable consequence is as the giant planets are growing, they're scattering out planetesimals from the solar nebula out. Now, these planetesimals get scattered out completely randomly. They're going everywhere. So there's no clustering here. If this process occurs in isolation, they just leave the solar system, that's it. But because the sun is now in a cluster, passing stars, and the tide of the cluster itself can perturb these orbits, in sort of a non-trivial way. Now, when an object gets perturbed, of course, two things can happen. It can just get stripped, right? It can just get stripped away from the solar system and it's gone. Or actually the perturbation can instead lower its eccentricity, because here the eccentricities are, in any case, close to 1. And if that happens, if you lower the eccentricity, then such an object gets trapped. And through this process, what gets created is the inner Oort cloud. Confusingly, the inner Oort cloud is not genetically related to the outer, the usual Oort cloud. right? And in any case, the inner Oort cloud must form in the cluster, while the outer Oort cloud must form after the cluster is gone. But that's a semantic point. Let's just, focus on the physics and note that if the sun forms in the cluster, then it's inescapable that you generate this this torus of debris that is removed in perihelion from the giant planets and is just sitting there. Now, we're currently not in a cluster. The cluster disperses on a time scale of 10 to 100 million years. And if there's no planet 9, then this picture that is shown in the middle panel is the full story. These orbits just get trapped, frozen in place, and nothing happens to them ever. But if planet 9 exists, actually what planet 9 can do is, with the help of passing stars and the galactic tide, unfreeze these objects. And what we asked ourselves during the first lockdown of the pandemic, this is Mike and I, is what happens to the inner Oort cloud if planet 9 is there, right? Can these objects contribute to the observational data? Because after all, we hadn't thought about this previously, right? In all our previous models, the observational data of the scattered disk of the Kuiper Belt was just drawn from the scattered disk. So we thought, what if some of the most distant objects are actually not scattered disk objects, they're inner Oort cloud objects that are being re-injected back into the solar system? As it turns out, that's more or less exactly what happens. So we began by making a self-consistent model of the inner Oort cloud. We modeled the sun's evolution in an Orion Nebula cluster-like environment modeled as a Plummer sphere, thereby creating the inner Oort cloud, and then subjected this inner Oort cloud, this population of perihelion removed debris, to long-term planet 9 induced evolution. And what we found is that indeed there is an efficient process of taking this stuff and re-injecting it back into the solar system, and observationally, it mixes in with the distant scattered disk. In other words, if you find an object at 500 AU, for example, with a semi-major axis of 500 AU like Sedna, you really don't know if that was a scattered disk object that got ejected out and then sculpted by planet 9's gravity, or was it a inner Oort cloud object that actually came from 3000 AU and got re-injected in? So why is it important? The reason it's important is that inner Oort cloud objects are dynamically younger. In other words, because they haven't gone through as many precessional cycles as the rest of the scattered disk, they don't cluster as well. So if we allow for these objects to get mixed in, actually our estimates of planet 9 parameters change. And as it turns out, we require a somewhat more eccentric planet 9 now than we thought. So this just goes to highlight the kind of iterative process that we have been engaged in during the first and second lockdown, of trying to refine our understanding of what we think planet 9 parameters really look like. And this is a kind of a visual representation of that. As you can see, particles initialized within the scattered disk, whose longitude of perihelion dispersion is shown in this black curve that looks kind of Gaussian, right? So that they almost perfectly anti-align with respect to planet 9, is indeed idealized when you compare it with the dispersion that comes from objects injected from the inner Oort cloud. It's clear that objects injected from the inner Oort cloud also cluster, but not as well. This is important. Okay, so at this point, I want to quickly summarize what we think about planet 9 and move on briefly to the scattered disk and its dynamics driven by Neptune itself. So first of all, the lines of evidence for the existence of planet 9 are the apsidal clustering, right? The fact that these eccentricity vectors align, right? It's the fact that that same population gets removed in perihelion. It's the fact that also all of these objects are tilted in the same way. The node and inclination also exhibit grouping, which is anomalous in the outer solar system. And then there's a whole population of excited high inclination bodies that also can be tied back to Planet 9 induced dynamics. And it's really been a continuous and iterative process to try and really estimate what the parameters of this object are. And the contamination that comes from the inner Oort cloud undeniably plays a role. Okay, in the last really few minutes or 10 minutes, I'll try not to talk too long about this, but I'm really excited about it. So please feel free to cut me off if I carry on too far. So really, in the end of this talk, what I want to do is go back to this picture and remind you that I made this, emphasis about the fact that only stable objects cluster together. And in any case, right, the fact that it's only the stable objects that are clustering together provides yet another reason why we think this clustering is real. It is impossible when you have a survey to look at the night sky, discover a point source of light and then say, well, that one looks stable, so I'm going to keep observing it, or say, well, that one looks unstable or whatever, right? The orbital stability is something that you can only estimate after you know the orbit, which takes years. So, given the importance of orbital stability in this entire Planet 9 question, Planet 9 story, the question we posed is, why are some objects stable and other ones unstable? Now, it seems like a stupid and simple question, but I would argue that it is a completely non-trivial question, because the standard way that people explain why some scattered disk objects are stable and others are not, they say, well, Neptune has a Hill sphere, which is about 1 AU. And if you get too close to Neptune, some number of Hill spheres away, then you are unstable. Neptune's gravity scatters you around. And if you're far enough away, then you're okay. So it's all about the perihelion distance. And there's a clear cut in perihelion distance at 36, or depending on who you ask, it's either 36 or 38 AU. Okay, so that explanation is wrong, okay? And you can convince yourself that that explanation is wrong really for two reasons. First of all, 8 is not a natural number of Hill spheres, right? You can, if it was like 2 or something, you could say, okay, that's what's going on. But really, right, 8 is a weird number of Hill spheres that you have to be away from to experience chaotic diffusion. Moreover, you can more dramatically convince yourself that this is not true by doing a simple n-body integration and putting an object with a semi-major axis of 2000 AU. And what you'll notice is that then the number is something like 20 Hill spheres. So this notion of like you have to get close enough to interact with Neptune is just not the right explanation. So what is it? Well, all chaos, according to Chirikov, which and he knew a thing or two about chaos, can be understood within the framework of resonance overlap. So in trying to think through what really sets the stability boundary of the distant scattered disk, it is important to abandon the picture of, oh, you fly and then you get close and you get kicked, and really reconsider, what are the underlying resonances that are driving the chaotic diffusion of the scattered disk. This is what we did in a recent paper that was just accepted. I guess it was published a couple of days ago. But before we go into the paper, I want to just remind you of something, right? That the simplest model for the resonances is the pendulum, right? For which the Hamiltonian looks like this top equation. It's very simple. And the width of the pendulum is controlled by this parameter k. Right? All I did here is I took this equation and made a contour plot setting k equals to 0.6. So the pendulum is perfectly integrable, right? But if we now imagine a kicked pendulum, which is kicked periodically, right, with a periodic delta function kick, then we no longer have a integrable model, and we have a perhaps the simplest model that exists of chaotic dynamics. So what this picture of the pendulum transforms into now is a surface of section where you can still recognize very well the pendulum structure that underlies it. But then if this number k, the width of the resonance, increases to the point where the neighboring islands overlap, then you have a chaotic sea. And this is the basic idea behind the Cherykov criterion, namely that the periodic kick splits this pendulum into a whole stack of resonances, and if they overlap, you get chaos. This is not anything new. As I put on this slide, this has been actually known since 1959, even though the commonly quoted reference for this is the 1979 review paper. Now, how can we take the scattered disk and reduce it down to something like the pendulum, which is kicked periodically, right? Intuitively, it feels like we should be able to, because, I don't know, Neptune's gravity feels like it provides a periodic kick to the orbit, and, you know, at least that part is there. So this is what we did. We said, let's imagine, first of all, that the orbit is in the plane. That's a pretty good approximation. Most Kuiper Belt objects have inclinations that are not too severely high. So let's imagine that inclination is 0, and model the scattered disk object as a test particle in orbit around a circular Neptune. So thus reducing it to the circular planet restricted 3-body problem. Okay, the circular planet restricted 3-body problem is not a new problem, okay? People have been studying this problem for hundreds of years. And the basic program by which you study this problem is you say that the Hamiltonian, right, is composed of the Keplerian part and the planet-planet interaction part, which is disturbingly called the disturbing function, okay? What is the disturbing function? Well, the disturbing function basically is just the planet-planet potential, and there exists an astonishing amount of literature on how to take this disturbing function, this 1 over r basically, and expand it in Fourier series and angles and power series and inclinations and eccentricities. And all of this analysis is beautiful, but the classical perturbation theory is derived in the limit of low eccentricities and low inclination orbits. This is clearly not what we have. Scattered disk objects have eccentricities of order 1. So unless we go to the computer, right, and do some kind of a closed form perturbation theory, we really are out of luck. So what can we do? Well, the other thing we can do is to abandon E and I as the small variables of the problem and instead treat the semi-major axis ratio as the small parameter. Okay? And this has been pioneered, I think, by the perturbation theory of Kalla back in the 1960s. And there have been iterations upon this, including the work of Rosemary Mardling in this decade. So by adopting the semi-major axis ratio of Neptune to the scattered disk object as a small parameter, we limit ourselves to only thinking about long period orbits. That's fine. That's what I'm interested in anyway. And we lift all restrictions on the eccentricity itself. And when we look at what the disturbing function looks like, it is indeed disturbing. It's a quadruple sum. And I usually make it a point to never work on problems that have sums because just like kind of unpleasant to deal with so many sigmas. But again, it was COVID, so there's a little bit more free time to just sit around and play with this. So here's what we found. We found that actually this expression can be reduced heavily. First of all, by limiting the order of the expansion to order 2, namely the quadruple order. It's common in secular dynamics to talk about quadruple order effects like the Kozai resonance, as opposed to octuple order effects like the usual Laplace-Lagrange coupling. it's more common in mean motion resonance studies to classify resonance as being first order in eccentricity and inclination, but there's no reason why we cannot do this with resonances as well. We can classify mean motion resonances by those that fall to quadrupole order, those that fall to octupole order, etc. So let's, for the purposes of simplicity, limit our expansion to quadrupole order. What does this do? This immediately sets a manageable limit on the degree of the expansion. And by the way, L and M here are just nothing other than the usual spherical harmonic, order and degree. This is taking the gravitational potential and doing a multipolar expansion of it. So we naturally can kill the first two sums. And that's pretty good. That still leaves us with two more sums, which is too many sums. So what about the third sum? Well, the third sum, the one in J prime, is linked to this quantity x, which is an integral defined function called the Hansen coefficient, which takes as its argument the eccentricity of Neptune. Okay, that seems like a lot, but by virtue of Neptune's eccentricity being very, very close to zero, we note something really cool. Namely, there's a property of these integral defined functions, which is that as the argument, the eccentricity itself, goes to zero, the function itself becomes of order the argument to the power, m minus j prime. If En is truly zero, which is the assumption of our model, then that means that the only term that survives is the one where j prime is equal to m. So that kills the third sum. So that's pretty cool, okay? And so at the end of the day, we were able to take that quadruple sum, expression and turn it into one that only has one sum. Okay, one sum is still too many sums. Okay, I hate sums, so especially infinite sums. So what can we do? Well, what we can do is the final step of this calculation is to recall that an infinite sum of cosines, j times m, where m is the mean anomaly, is just a Fourier expansion of the delta function. So as a result, what we can do is we can turn this expression of the disturbing potential into a kind of periodically kicked set of resonances. And as it turns out, to my surprise, the resonances that dominate the quadrupole order are 2 to j mean motion resonances with Neptune. Okay? In other words, Neptune's gravitational kicks are nothing more than an infinite series of 2 to j mean motion resonances. Through this analysis, we've been able to reduce the Neptune scattering problem to effectively the same thing as the Cherenkov standard map. And from this, and this is, I'm of course skipping over a couple steps, this is a paper that I'll put up on the archive in the next couple days, but from this, we've been able to derive an analytic stability boundary of the distant solar system and compute its diffusion coefficient and semi-major axis also from entirely analytic grounds. And it turns out that this matches the numerical calculations relatively well. And indeed, there's a hidden semi-major axis dependence, which was not previously recognized. Okay, I think I'll skip, I'm kind of at the hour here. So I think I'll stop here and take any questions. Thank you for your attention and for listening me talk at length about Planet 9 and the scattered disk.
Okay, thank you very much for your talk. Well, that's an incredible capability of reducing sums.
Yeah, that's right. It's one sum is too many sums.
Yes. So I have a very naive question to start. So you mentioned that you about Planet 9. Actually, you don't know if actually it's a planet. You only know that it has 5 masses, Earth masses, right?
Yep.
And
That's right.
you have a prediction of the orbit, right?
That's right.
So can you estimate with the current facilities the probability, or how much time would you need to detect this?
Yes.
This guy.
Yes.
Let's say.
Absolutely. So when we first started, we decided we needed 20 nights on the Subaru telescope, the Japanese National Observatory, to kind of cover the 1 sigma, to cover sort of the 1 sigma region of where Planet 9 can be. We've actually done more than I expected we would complete. We've completed a little bit more than half. The short answer is we haven't found it yet.
Okay.
Of course, we've also been simultaneously taking advantage of kind of existing data sets. So Mike, there's a paper that Mike led that just he put it up on the archive maybe last night or 2 nights ago, where we used this wiki transient facility. This is data that's being collected every night at Palomar to look for Planet 9. Unfortunately, it's only sensitive to the closest possible orbits, so to speak. So we, again, didn't find it. It's not really a surprise because those orbits were so close that they would have violated the spacecraft data anyway. But it was one of these things where, so it's in itself an iterative process. But the good news is the Vera Rubin Observatory is coming online, and that's going to be a game changer, right? So I suspect, my hope really is that Vera Rubin will just find it, and that'll be the end of this kind of these types of presentations, and at least if not, Vera Rubin will discover a lot more of these distant Kuiper Belt objects, and that'll help narrow down the parameter space a lot.
Yeah. Now I have another more weird question. They say, is there any weird theory of what this object is? Like, well, it's not a planet, maybe it's not emitting, or I don't know.
Yeah, it's a good question. So there are indeed there's a number of theories actually. Point is, of course, as I said, because what is happening here is secular dynamics. This can be anything. This can be a 5 Earth mass burrito, a 5 Earth mass hamburger, distributed, over the orbit. Like all of that is allowed. There's a group out of University of Illinois who proposed that this is a primordial black hole. I'm not really a cosmologist, and when I say I'm not really a cosmologist, I'm just not a cosmologist at all. Actually, I don't know anything about cosmology, but my understanding is that if the number density of primordial black holes was high enough for Planet 9 to be a primordial black hole, we would have other problems with microlensing and such. But, it does point to an important point, which is that really this gravity could be coming from anything. So if we think about weird things like, could the sun have some dark matter halo that's asymmetric? I'm just making that up, but like, anything.
Small dark matter or something.
Yes.
Clouds.
Right.
I don't know.
Yeah, and there are like caustics, right? Like people do talk about dark matter caustics that are a few Earth masses. Not that I know anything about dark matter, which I don't.
And what are the possibilities that, I don't know, maybe it's emitting? Because this case is like a black hole or dark matter is not really emitting, but something more realistic, like, I don't know, gas, dust, something like that. Happens to be there, emitting in another wavelength.
Yeah, and people have sort of looked for it with this is like some cosmology telescope that observes in the right wavelength for a planet that's about 40 Kelvin. Unfortunately, they were only able to rule out Planet 9 where we already know it's not. But it is an interesting thing to look for. And of course, if you were to go and visit Planet 9, it would entirely be dominated by its own, internal emission, right? The reflected light is tiny, which is why it's like magnitude 24. So it's quite tough.
Yeah. Okay, I will leave time for other questions now. So Reinaldo, you can ask your question.
Thanks, Konstantin, for the talk. It's very fascinating. I have one question about the last part you showed. I would like to gain some more physical intuition about this process of interaction. But first, I will bring two questions that appeared in YouTube. So the first one, Gabriel Rodriguez Riquel, he's following your seminar. And he says, very nice seminar, but I'm still skeptical of this hypothesis. He means about the existence of the planet, I understand. So his question is, why has an object of this size still not been found, especially by all-sky infrared surveys?
Yeah, the short answer to that is it's very, very dim. When you look at all-sky infrared surveys, like WISE, for example, they are completely not sensitive to something this far away. There has been a NeoWise, reanalysis to look at out to what distance could you constrain Planet 9, and it turns out that it's only marginally useful. Now, basically, as a result of this, because infrared is not the way to go for this object, you have to look for it invisible. And my hope is that an all-sky, or at least a quasi all-sky survey like Vera Rubin will discover it. Okay, but even so, I mean, magnitude 24 is really, really dim, right? I mean, I did not have an appreciation of this until I started observing myself. And, observing is one of these things where, like, you don't quite know what it's like until you try it. And I absolutely hate it, right? It's just completely, it's such hard work because, at the end of the day, you don't know what you find, and like weather controls your, weather controls the outcome, which is frustrating. But, we, in our entire, Subaru survey, right, we've only discovered so many objects that were even worth following up, just because it gets so dim. Yeah, so the short answer is flux. Reflected sunlight goes 1/r to the 4th, and if you put a object only a couple times the radius of the Earth out at 600, 700 AU, it's really, really dim.
Thanks you, Konstantin. Thanks, Gabriel, for the question. And there is another question by Luciano Silva. First, he says, your talk was spectacular. Congratulations. And he asks, are your simulations done on small machines, for example, laptop with Python, or on some infrastructure with high performances, such as clusters?
Yeah, so it's both. What I like to do is I like to build a hierarchy of models, going from the most simple models that I actually just you barely need a computer for, to the kind of maximally realistic ones. And the maximally realistic ones I do on the cluster at Caltech. They're not so computationally heavy that they require something huge like one of the national level clusters, but they do run for a while, a month or two at the worst, for the most kind of heavy models. But I find it important indeed to actually have a hierarchy of models, because I don't understand the most complicated models unless I start with the simple ones. And I can't really make sense of what's going on when all the orbits are kind of just dancing around. If that's so that's not the way that I prefer to do things.
Thanks, Konstantin. Thanks, Luciano. Gabriel Riquel, who made the first question, he He's saying thank you for your reply. And I myself, I have two questions. I try to pack them together. It's I think it's very simple, but I would like to gain more intuition. When you explain about this interaction of Neptune with these bodies,
Yes.
this scattering interaction, I have no idea. Let's say this interaction, does this take a lot, many orbits to take place, to scatter the body, or it happens in just like a one approximation, or it takes several?
So it's a diffusion process ultimately, where the diffusion time step is an orbit, but of course to gain any meaningful progress, you need many orbits, and so one of the things that we realized, this was maybe something we should have guessed right away, but after doing the calculation, we said, okay, now we can estimate the Lyapunov time analytically. And we estimated the Lyapunov time, and we got the orbital period as the estimate. And we thought, how can this be? But of course it's the orbital period, because the orbital period is, if you were to take a bundle of trajectories and launch them on the same orbit, right? As they pass Neptune, they would all sample Neptune at a slightly different phase, and that's the characteristic time scale over which their linearized phase space distance from one another would begin to diverge. So it's both. It's one of these things where the kick time scale is the orbital time scale, but it's not the case that, okay, you are flying and you get kicked once you're out of the solar system. It's a walk out of the solar system.
Oh, thanks.
Like a slanted walk, actually. Yeah.
It's very clarifying. So I understand that the theory is averaged by the orbits, right? To make the theory, you average of orbital time.
Yeah. So no, it's not a secular theory where you doubly average. Yeah. It is a resonance theory. Yeah. It is a resonant theory, and what we found is that at the quadrupole order, the potential is just a series of 2 to n resonances, right? An infinite sequence of 2 to n resonances, and that infinite sequence can then be reduced to the kind of Cherenkov standard map-like picture. But the other way to think about it is that the orbit, right, is resonating with the, right, the orbit sits in a forest of 2 to n resonances, and the perihelion distance controls how wide each one of those resonances is. So closer than a critical perihelion distance, right, the resonances overlap and you drive a chaotic layer. And that has that's where that weird equation with the logarithm and the semi-major axis ratio to the 5/4 power comes from. It's from doing that analysis.
Thanks. The last part of my question is very short. Does this interaction involve a lot of energy exchange, or not too much? It's just scatter, I don't know, the direction of the body? Because I saw some bodies migrating to coming to inside the system.
It drives a stochastic migration. So it does indeed, it instills a random walk in energy, which is constrained by the Jacobi constant. But the Jacobi constant for this problem, actually, if you take the limits of E close to 1 and coplanar, it just turns into constant perihelion distance. So the way that you can think about it is, Neptune's orbit is a circle, and every time you come in, you roughly keep the perihelion distance the same, but the aphelion walks around randomly. Okay?
Thank you.
Okay, so we have a question by Guilherme.
Hello, Konstantin. Sorry, I guess we are running out of time, but if I may ask some questions, I had several, but you answered some from Maria Vitoria's questions as well. The first one, I guess, would be, you mentioned that out of the NPOs, objects known, very few have the detailed orbits constrained, let's say. I guess this is some kind of observational limitation because you cannot like obtain a precise astrometry for a lot of these objects. My question is that the case? Is that I know nothing about observations in the solar system. So is that the case that to obtain an astrometry of such kind of objects is that difficult that we only have just a few with detailed orbits calculated?
No, so I should have been clear by what I meant by detailed orbits. We know the orbital elements well, but only a few of them we know the biases. So where the surveys look, because usually when you're looking for them, you find some Kuiper Belt objects, you publish them, you say, okay, I've discovered them, and move on with your day, right? And only a couple surveys have done this, meticulous thing of keeping track exactly where they looked. One of them is OSOS, and it's actually an extraordinarily biased survey because it's a pencil beam survey. So, there you actually know, you keep observing the same part of the sky, basically, so you kind of know what you're discovering. The other one is DES, which has this weird tank-looking, so I'm saying that the objects that came from those extraordinarily well-characterized surveys, right? If you just play with those 14 data points, right, you can't really do good statistics with it. Not only because there are only 14 data points. I remember even in my in college, in my economics class, okay, and which should tell you a lot, right? My economics class, somebody said, unless you have 20 companies, you don't know like what's happening. Like 20 companies is the minimum number of companies that you need to make some inference about the economy. And I remember that's like some statement about the minimum number of N that you need. So that basically all I'm saying is that if you limit yourself to that sample, it becomes a not very definitive or really interesting like statistical exercise. Also, because in order to have perfect control over your biases, you have to bias yourself a lot, right? You have really good control if you only have a survey that looks in one spot, right? So this is true. If you look all around, your bias control kind of goes away. So as a result, I guess the point I was trying to make is that there's a conflation between inability to detect clustering with proving that clustering is there or not. Okay, I think that's a conflation that's very much present in the literature.
Yeah, okay, thank you so much. That makes a lot of sense now. The other question that I had, since you mentioned the hypothesis of like a primordial black hole like this, I was, throughout the talk, I was imagining like possibilities, like small dark matter subhalos flying by the solar system, which would be kind of, I think, even crazier because given the nature or the expected nature of dark matter. But what I thought would be the most plausible, but you actually mentioned that this cluster is actually, it lasts a lot, like very long living cluster, so it's not from the primordial formation of the solar system. But I was wondering, what if the solar system or the sun was born in an open cluster, and then this open cluster could live for I don't know, maybe 1 billion years until it is tidally disrupted and destroyed, and then I don't know if the signature of the cluster could remain in this situation with a star inside the star cluster. Like,
Great
I don't
question.
know.
Great question. I thought about this back in 2020, or I guess back in 2019. And in fact, I wanted to know the following quantity. What is the closest distance at which a star has flown by the solar system? Okay, which relates very much to your question, because if you live inside of a globular cluster or an open cluster that is particularly long-lived, just by n sigma v calculation, you develop closer and closer approaches. Impact parameters go down in time. The answer is 230 AU. And this answer comes not from the most distant parts of the Kuiper Belt, but instead from the cold population. And there's a different subset of Kuiper Belt objects which live between 43 and 47 AU. And these objects are extremely thin. Their inclination dispersion is only 1.7 degrees. And what we showed is that if you have, if you live in a cluster too long, then you disrupt that thin disk of cold KBOs. So you can't invoke that. You can't invoke the cluster as a source of perturbations for a long time.
You would kind of dynamically heat this thin disk of Kuiper Belt object. Okay, I understand.
Correct.
Okay. Yeah, and the last question is more like another speculation, but I think a more farther one, not about the nature of Planet 9, but have you thought about what is more likely for us to discover an analog of Planet 9 as an exoplanet with like the future generation of radial velocity surveys that will reach like centimeter per second precision, or to find the Planet 9 in the solar system?
Well, the answer to that is the first is more likely because it's already happened. There's some, I forgot the license plate of this planet. It's some stupid license plate like HDU 1678910. I don't know. Anyway, there's a license plate of some planet which is almost an exact Planet 9 analog in terms of orbit. I remember I saw this because I saw this on the news. Like that came up on my like New York Times feed where like, oh, like astronomers discover Planet 9, like something. I said, what? I look into the thing. It was some stupid exoplanet. But the point is, the exoplanet is just like the Planet 9's got the right orbital parameters. So this goes to show that the existence of objects with such orbits is not insane, right? There is a natural process that produces them. Whether or not that happened in the solar system is we're going to see.
Okay. I actually will look into the literature to find the paper that describes it.
Yeah. Thanks.
Thank you so much.
Okay, so we will thank again Konstantin. Many thanks for your talk and for the discussion. It was extremely interesting. And
Thank you, Maria.
I will also thank who is following us and also the people in YouTube. Many thanks for your participation. And well, Konstantin, do you want to say something more?
Oh, I just want to say thank you for inviting me to give this talk. It was great to meet some of you in 2 dimensions, as well as to see some familiar faces. Hi, Silvio. It's great to see you again in 2D. Hopefully, we'll see each other in 3D at some point in the future. And this, of course, goes for everybody. It was a real pleasure, and I hope that once this pandemic ends, we will grab a beer in real life.
Sure.